After 200 years from its invention, we can now say that reinforced concrete has been considered a truly dazzling material. But its fantastic properties, I believe, created a frenzy that pushed professionals to overlook its drawbacks, and that still doesn't allow us today to rationally discuss the significant negative impact it has had on architecture. Reinforced concrete is a golden material indeed, but like King Mida in his myth, what he believed was the ultimate blessing, it ultimately became his curse. The Industrial Revolution demanded stronger, faster, and more economical ways to build large infrastructure projects, but traditional materials had limitations, and the overwhelming and inescapable nature of progress in the Victorian era was not willing to compromise. Hello Masters, and welcome to the Guild. Concrete is now ubiquitous, but it has actually been around for thousands of years. Concrete began as early mixtures of burned limestone, sand, and water used by ancient cultures such as the Nabateans, the Egyptians, and also the Chinese, who gradually discovered how hydraulic lime and pozzolanic materials could harden underwater. My fellow Romans then transformed these early recipes into a true concrete technology, using volcanic sands like the pozzolana. And these enabled them to build durable structures like the Pantheon, a 43 meters high building built nearly 2000 years ago, and that still stands today as the largest unreinforced concrete dome in existence. Pretty remarkable. However, these ancient materials has little resemblance to the one we pour today. We now know that Roman concrete, the opus caementicum, hardened through a chemical process between lime, volcanic ash, and seawater. Following new excavations in Pompeii, archaeologists discovered a near-perfectly preserved concrete workshop, complete with dry, pre-mixed piles of materials and marks on the walls detailing the quantities. What more do you want? Recent chemical analysis from MIT found that contrary to what was previously believed, Romans used a hot mixing method involving quicklime, calcium oxide, which in Italy we call calce viva, live calcium, an extremely caustic and unstable material. It seems instead that slaked lime, the hydrated lime, was used just for finishing mortars and plasters, where contact with skin would be unavoidable. This means that the chemical reaction would heat up part of the concrete as it set. Studies have found that this mixture grows stronger over time and also has some self-healing properties, where the fragments of lime, called clasts, that remain in the concrete after it sets, dissolve and recrystallize when wet, with the concrete's pores and cracks strengthening its microstructure. Ancient Roman concrete extensively used local materials, and its exact composition varies significantly based on the resources available on the construction site. Roman engineers, in fact, adapted their recipes to different regional geological contexts, a practice also described by Vitruvius. For example, in regions where suitable volcanic ash was not naturally available, such as Britain and other non-volcanic areas, Romans adapted the formula by grinding down local materials like tiles or bricks and adding the powder to the mixture to achieve a similar binding effect. They also perfected mixture used in structures that required special properties. For example, in marine structures, like piers and harbors, Romans add seawater to the mixture, which they found reacted with the volcanic ash to form rare strengthening minerals, like the aluminium tobermorite, making the concrete stronger over time. They also invented a concrete with waterproofing property, the opus signinum, which used small pieces of broken pot instead of other aggregates, used mostly for Roman baths, aqueducts, and cisterns. Modern concrete instead is an entirely different invention. It relies on Portland cement, called Portland because its hardened form resembles the pale limestone quarried from the Isle of Portland here in England, and steel reinforcement, which become more available with the Industrial Revolution. A miraculous combination where two different materials compensate positively for each other's weaknesses. Traction and contraction give an incredible performance that allowed concrete to become ubiquitous and architects and engineers to challenge common sense. But not all is gold that shines. Like Dorothy in The Wizard of Oz, we must start our journey finding the truth at the end of the road, and not blindly trust authority, but pulling back a curtain to find the truth. But before we do, please like the video if you enjoy these topics, add a comment sharing your opinion and suggestion for the channel. And don't forget to subscribe, this helps us a lot. Thank you. Reinforced concrete was invented in 1853 by a plasterer from Newcastle called W.B. Wilkinson. Wilkinson inserted steel hoops into wet concrete to resist the tensile forces that cause concrete to crack under the load. From this humble origin, reinforced concrete would soon become the go-to material for rapid and economical construction. But contrary to the structures of the ancients, modern concrete buildings are not designed for longevity. Studies show that the typical structure has a lifespan between 50 and 100 years. This is the estimated period during which the structure is expected to remain safe and functional, and assumes routine maintenance. This lifespan shortens significantly for structures exposed to salt, humidity, vibration, or physical and thermal stresses. Modern additives used to speed curing, because of course we can't wait 28 days for nature to do its thing, or to make the concrete less permeable or resist to corrosion, etc., if not carefully designed and properly executed, can further shorten its durability and performance. And now maybe you might think,
wait a minute, by the time I finish paying the mortgage for my flat, I might have to demolish it?
Well, reinforced concrete structures are typically designed for a service life of 50 to 100 years. So this will probably be a problem for your kids or grandkids. But if you consider how the lease length affects the value of your home, imagine what this will do when your kids want to sell your old building. And we don't pay cheap our buildings. While plain concrete can literally last for centuries, modern reinforced concrete deteriorates much faster because the steel bar inside inevitably rusts, causing cracking, spalling, the so-called concrete cancer, and structural failure. And because concrete structures work as a system with a solid bond, parts can't easily be replaced. Yes, there are corrosion mitigation technologies and alternative reinforcements, but they cannot solve the fundamental flaw of embedding the steel in the concrete. Our society must rethink its assumption about materials and go back to building structures that can endure far longer and avoid waste of material, money, risk to lives and health, as well as the continued erosion of our relationship with nature. But if you consider what we were capable of building using no magical material but on ingenuity, I'm pretty sure we'll be fine. If this fervor and ignorance were somewhat excusable at the end of the 19th century, now it has become a willing blind eye, a complacent system that puts quantity over quality, and it's willing to ignore what we know and still allowing this material to be the backbone of our world. Highways, towers, stadiums, dams, ports, pipelines. Most of the built environment rests on reinforced concrete, relying on its magical performance even when it would not be required. Our modern cities, in effect, have all been constructed with an expiry date. As mentioned, the problem is straightforward. Concrete and steel, they love each other at the beginning, but want to divorce later. They age badly together. Steel corrodes, expands, and fractures the surrounding concrete. Carbonation reduces internal alkalinity. The moisture infiltration accelerates degradation. Temperature cycles open microcracks. Chemical reactions like alkali-silica reaction destabilize aggregates. But are architects taught this at university? From talking with colleagues, I often find that no, they're not aware of this itsy-bitsy problem below and above our heads. The worst part is that structural concrete is boxed behind walls or hidden from view, and this doesn't allow assessment of these failures, which accumulate quietly and invisibly. And when so-called old buildings need to be renovated, more often than not, the most cost-effective and safe strategy is to gut the building and keep the facade, if of any relevance, or demolishing it altogether. But even the new structures are in concrete, pushing the can again down the road for the next generation to solve. The global replacement bill will be measured in trillions, not millions. The next generation will inherit a crumbling urban fabric that must be dismantled and rebuilt completely. Hopefully they will be wiser and not build it in reinforced concrete. We all must relearn restraint, humility and moderation, as another problem of reinforced concrete is that it has enabled ever larger structures, which again will pose a real problem very soon. Imagine this. Now developers take a site with a few homes and make a big tower. The current few people living in those little homes are relatively easy to ask to move, but when the tower must be replaced because it's in reinforced concrete and eventually its structure will fail, who is going to have the resources to displace all those people who bought flats in towers? The longevity problems of concrete are huge, but only one side of the issue. The environmental footprint of concrete is severe and escalating. Concrete is the most used material in the world after water, with a global consumption of around 3 tons per person per year. Modern concrete production depends on sharp, angular sand from rivers and coastlines. Desert sand, rounded by the wind, is unusable. The result is a global extraction at a scale that is destabilizing entire ecosystems. Riverbeds deepened, triggering erosion and flooding. Coastal environments strip of protective sediments. Illegal sand mining linked to organized crime. Entire islands are disappearing in Southeast Asia. Sand is now the second most extracted resource on Earth after water. Cities are literally built on the destruction not just of the nature they replace on site, but also of distant landscape. As you know, producing concrete is also water intensive. 1 ton of material can consume up to 300 liters of fresh water. Imagine what this entails for arid regions that have been building as crazy for decades. To mask and diffuse facts, the industry now promotes green concrete. Concrete production is in fact a major source of global CO2 emissions. The term green concrete often refers to minor improvements such as using waste materials as components, like fly ash or slag, or incorporating captured CO2 during the mixing process, which only marginally reduces the overall impact of a fundamentally high-polluting industry. The industry is exploring various technologies to electrify cement production, but this is very difficult and poses several challenges, especially the high temperatures required for the calcination and the need for efficient heat distribution. But in my opinion, the main issues explored so far will still remain intact even if it's completely electrified. Though I guess every little helps, but knowing modern humans, this will become the excuse not to face the other challenges and to keep business as usual. The material is not being reinvented, but its public image is. As with everything in modern culture, all is narrative and very little is substantial. The good news is that if longevity and ecological responsibility matter, as they should, the alternatives to concrete already exist, not in new expensive high-tech materials, but in traditional methods of construction, which we blindly abandon to express our ego and make more profit. Stone, brick, timber, and earth-based construction can all have a place in our cities, and they can help us making them more resilient. They have characteristics that reinforced concrete cannot replicate. They are repairable, they age predictably, they can last centuries, they use minimal energy to produce and can be local, and leave no toxic legacy. But this will only work if designers are sensible and don't ask them to build the impossible. We must once more learn from the material and ask, as Louis Kahn did, what do you want to be? And work with it, not against it. We must accept reality. Modern methods of construction really are inefficient. If you scrutinize them, they all require over-engineering, and even materials that could support themselves are all hung. If we want resilient cities easy to maintain and sustain, with human densities that allow localized intervention and don't strain the infrastructure, we must stop pretending that reinforced concrete can be dressed up as sustainable. In my opinion, the path forward lies not in marginal technological tweaks, but in rediscovering material systems that work with time and are not ticking bombs. See you next time.